Hello, my name is Luis Gustavo de Medeiros, and my partner was James Russo, and our project is titled Monte Carlo Tree Search Connect 4 AI. So we decided to make an AI player for the game of Connect 4. Connect 4 is a turn-based perfect information game, and similar to tic-tac-toe, the goal of Connect 4 is to connect 4 pieces in any direction. There are over 4 trillion possible states, and Connect 4 has a maximum branching factor of 7 moves usually. So the software we wrote, we created a command line based implementation of Connect 4 in Java, and we made it so it was easy to create new bots. You only need to implement abstract player class and get move method, and we used our own tree class for tree data structure and no external dependencies. We wanted to see how well AI bots performed in the game of Connect 4, so we implemented 2 bots. One is an n-random simulation bot, and the other was a Monte Carlo tree search bot using upper confidence bounds. We then played the 2 bots against each other and against human opponents. So the first bot we created is using an algorithm of n-pure Monte Carlo search, which in each turn, the bot plays out n random simulations from each possible moves, and it determines which move has the highest win percentage, and it takes the move with the highest win percentage from these random playouts. The other bot we implemented was Monte Carlo Tree Search. So Monte Carlo Tree Search employs an algorithm in 4 steps. So at each turn, you start at the root node, then recursively select optimal child nodes until leaf node is reached. If the leaf node doesn't end the game, then you create 1 or more child nodes and select one. At that child node, you run a simulated playout for this children node until result is reached, and then you update the current move sequence with the simulated result. So you basically backpropagate the results up the tree. You do this for a certain number of iterations, which we set to greater than 10,000. In order to select an optimal child, node selection during tree descent is achieved by choosing the node that maximizes some quantity. And this is analogous to the multi-armed bandit problem, in which a player must choose the slot machine that maximizes the estimated reward each turn. So each node has an associated value with it, and the value used was an upper confidence bound, which has a formula of the following result. So it is vi plus c times the log of n, or the square root of the log of n divided by ni, where vi is the estimated value of the node, ni is the number of times the node has been visited, and n is the total number of times that its parent has visited. C is a bias parameter that you can tune. Vi is just the win percentage, so it's the total number of wins over the total number of visits to that node. So the formula on the previous slide balances both the exploration of unvisited nodes and the exploitation of no nodes and rewards. You can change this by changing the C factor, so as you increase C, you'll explore more unvisited nodes, and as you decrease C, you'll explore nodes with higher playout values. Balancing these 2 factors is important, as node values are based on random playouts and thus take several iterations in order to accurately converge. So Monte Carlo Tree Search has several advantages. It does not require any domain-specific knowledge, only requires knowledge of possible moves and terminal states. You can easily port it to several other games due to its heuristic characteristics, and it performs asymmetric tree search, visiting more interesting nodes more often. It's easy to implement and suitable for games with large branching factors such as Go, Chess, and Connect 4. There are some disadvantages though. It can require a huge number of iterations in order to find reasonable moves, due to the fact that games with high branching factors have huge trees and thus many nodes may not be visited often enough in order to provide accurate estimates. This was not a problem in our implementation though, because Connect 4 only has a branching factor of 7, and thus we were accurately able to, within under 10 seconds, evaluate moves. Another disadvantage is that playouts are random, don't accurately reflect initially the nature of rational agents, and in its basic form does not incorporate any domain-specific knowledge, which can yield significant improvements in certain games. So similarities and differences between the 2 algorithms. So you play out random simulations of the same move multiple times, and you compare relative strength of moves. However, Monte Carlo Tree Search uses a game tree, not just random simulation, and Monte Carlo Tree recursively applies pure Monte Carlo search on the tree. So some statistics we used were win percentage versus opponent and average number of turns to win. So win percentage of two, in this graph, we can see the win percentage of two pure Monte Carlo AIs versus each other. So one of them has just pure random playouts, and the other one has, and the one on the y-axis has random playouts. But if there is a winning move, the AI takes it. So we can see that the one with the modification has a slight edge and has an approximate win percentage of around 55% as you increase the number of playouts. So this is the win percentage of Monte Carlo tree search against a pure Monte Carlo with n equals to 4,000. So we can see as we increase the number of iterations, our Monte Carlo tree search player becomes very good, winning an overall winning around 60 to 70% of the time when starting first. And we can see in an overall win percentage is around 70 to 80% against the other AI, which is very good. So yeah, in conclusion, the two implemented Monte Carlo search AIs are hard to beat and run very quickly. Both implementations can easily be ported to other games and are easy to reason about, and Monte Carlo tree search AI could be made better by incorporating Connect 4 specific knowledge into them, such as more reasonable gameplay into playouts, and by parallelizing the algorithm, increasing the number of visited nodes. The next step we would do in order to make it a better algorithm would be to create an opening playblock with perfect play, as most Connect 4 games are decided within the first couple of moves. And the first player only has one winning move, which is the middle column. So now I'll show you a demonstration of the algorithm. Let me just open up the terminal. So our game is compiled from give me a second. Our game is compiled from the command line, and so if we just run javac game board.java, we can compile our game. Or I mean, just javac game. And then if we run java game, we can see a current game. So in this game, I had a Monte Carlo tree search AI play first, and then another pure Monte Carlo bot play second. So yeah, so on average, player one wins a lot, and since the parameter I used in this one was more than 10,000, player one will always win. So yeah, if I so I can easily create a game against a human player. So let me just do that. And then we can easily recompile the game and run it. So yeah, we can see that as the AI bot plays, it shows me the number of times each possible move has been visited in our game tree, and the most promising opening is the middle column. So yeah, if I can enter a column number for my move, and then it thinks, and then it plays, and then here, gameplay continues like this, and then I'll block his win. You can see the AI bot thinking. Then I'll block his attempted win again. And I'll play until gameplay ends. And you can see he won, as I had to either block his move and let him win by making that diagonal, or if I didn't block that move, he would have won by having gotten 4 in a row horizontally. So yeah, and so we can also play, you can easily play in the game by modifying and having 2 human players, or you can easily modify the game to have 1 human player or 2 AI bots. Here is me playing against myself, and then you can easily see player 2 won.